To illustrate the estimation of VAR models, we will use the Canada dataset available in the VARs package in R. We also used this data in the earlier tutorial to show the determination of lag length in VAR models. The Canada dataset includes data on 4 macroeconomic variables from the first quarter of 1980 to the fourth quarter of the year 2000, that is, it is a quarterly dataset consisting of 84 observations. The variables in the dataset are employment, labor productivity, real wages, and unemployment rate. We will include all 4 of these variables in the VAR model, that is, we will have 4 endogenous variables or K equals 4. We will not make any seasonal adjustments because there is no seasonality in the variables. However, we will discuss how to include seasonal dummies and specify exogenous variables in the VAR model if needed. It is important to note that we usually estimate the VAR models with stationary variables. In case the variables are non-stationary, we check for cointegration and apply VACM model, or we can sometimes estimate a VAR model in differences. If the variables are integrated of order 1 or I1, then we can consider estimating a VAR in first differences given that the variables are not cointegrated, that is, they do not have any long-run relationships among each other. Stationarity and order of integration can be easily determined using tests such as the ADF and KPSS test. Here, we will not go into the details of stationarity or order of integration. We will focus on the estimation of VAR models in R and Stata. In R, we can use the VAR function provided by the VARs package for estimating VAR models. In the command shown here, we first input Canada, which contains the dataset with our 4 variables under consideration. The P option is used to specify the lag length or the number of lags to include in the VAR model. P equals 2 means that the function will estimate a VAR2 model or a VAR model with 2 lags of each endogenous variable as independent variables in each equation. The type, season and exogen options in this command are similar to those in the VARSelect function. The option type can be used to specify the constant or trend that we want to include in the VAR model. Type equals both means that we are including both a constant and a trend in the VAR model. Additionally, we can specify type equals trend for trend only, type equals const for constant only, or type equals none for a VAR model without constant and trend. The season option can be used to specify and include seasonal dummies in the VAR model. Here, we do not need to make seasonal adjustments because the variables do not exhibit seasonality. So, we can exclude this option or specify null. If we wanted to include seasonal dummies, we can specify the length of the seasonal period in this option. We do not need to create any seasonal dummy variables manually, we simply need to input the frequency or length of the seasonal period. The function will automatically create and include centered seasonal dummies. For example, the Canada dataset is quarterly, so we can specify season equals 4 if we wanted to include quarterly seasonal dummies. Similarly, we can specify season equals 12 for monthly data to include monthly seasonal dummies. Apart from these, we can also include exogenous variables in the VAR model using the exogen option. In Stata, we can use the VAR command to estimate the VAR model. In the VAR command, we first specify all the variables we are considering in our VAR model, which include E, prod, RW, and U in our example. The lags option can be used to specify the lag length or the lags to include in the VAR model. Lags 1 by 2 specified here implies that we are estimating a VAR2 model or a VAR model with 2 lags of endogenous variables. Stata also provides us an option to handpick the lags we wish to include in the VAR model. That is, we can specify the exact lags we want and drop certain lags of variables. Suppose we only want to include the first, second, and fifth lag of endogenous variables in the VAR model. In such a case, we can specify lags 1 to 5 as shown here to include only the first, second, and fifth lag in the VAR model and skip the third and fourth lags. The exog option can be used to specify any exogenous variables we are considering in the VAR model. We have specified exog t to include a trend in the VAR model, similar to the varsoc command. Stata does not give us a separate option to specify trend in the VAR model. However, if we want to include a deterministic trend, we can do so using the exog option as shown here. The variable t is simply the time ID for trend from 1 to 84 because we have 84 observations. Moreover, we can also include seasonal dummies using this exog option to account for seasonality. However, we have to create the seasonal dummies ourselves and specify them in this option. For instance, our Canada dataset is quarterly, so we can create quarterly seasonal dummies and specify those in the exog option. Now, let us take a look at the results of our VAR model. The table shown here contains the results of a VAR2 model with constant and trend that we applied to the Canada dataset with k equals 4. As we can see, the lag length of this VAR model is 2, so we have coefficients for the first and second lag of all the endogenous variables. The first thing that you will notice is that many of the coefficients for the lags are not significant. This can happen in VAR models, especially in large systems with many endogenous variables and lags. To check whether the model is a good fit, it is usually better to rely on other methods instead of the number of significant coefficients in VAR. For instance, the VAR model residual should be white noise, and we can also rely on the value of information criteria as compared to other VAR specifications. The VAR models try to describe the underlying DGP or data generating process, and often we are not interested in the VAR coefficients themselves. Instead, VAR models are mostly used for forecasting, FEVDs, and impulse response functions or IRFs. These results and coefficients can be visualized in the matrix representation of the VAR model that we discussed in earlier tutorials. Since our VAR model includes a constant and trend, we have included the constant and trend in matrix representation as shown here in blue and green. The coefficient matrices for each lag are 4x4 matrices because we have 4 endogenous variables. The first row of the coefficient matrices belongs to the first equation or the employment equation of the VAR model. The second row of coefficient matrices shows the coefficients of the second equation or the labor productivity equation of the VAR model, and so on. The first coefficient matrix represents the coefficients of the first lag of all the endogenous variables in each equation. Similarly, the second coefficient matrix shows the coefficients of second lag of the endogenous variables in each equation of the VAR model. If the variables are non-stationary and not cointegrated, we can use a VAR in differences. If the variables are cointegrated, then we should use the VECM model or other models that can incorporate the error correction mechanism. Suppose the variables are not cointegrated and are I1 or integrated of order 1. In such a case, we can consider a VAR model in first differences. In R, we can slightly adjust how we specify the dataset in the VAR function. In the command shown here, we have used the diff function within the VAR function to take the differences of all the endogenous variables in our Canada dataset. The option differences is used to specify the order of difference. We have specified differences equals 1 to take the first difference of the variables. Similarly, we can specify differences equals 2 to take the second differences. It is important to note here that we have changed the lags and trend specification in this VAR model in first differences. Earlier, we estimated a VAR model with 2 lags and also included a trend. Here, we have specified p equals 1 in VAR in first differences. We have reduced the lag to 1 because we have taken the first difference of all the endogenous variables. When we take the first difference of variables, the linear trend is eliminated from the variables. This is why we have included only a constant in VAR in first differences using the option type equals const. Another thing we must keep in mind is that taking first differences of variables means that our VAR model is now a short-run model. The estimated coefficients will be short-run coefficients because the first difference means how variables change between time periods. The focus is not on the original variables and levels, instead the focus is on the short-run change in variables from one period to the next. If you have to take second differences, you must further reduce the VAR lags by 1 and also remove both the constant and trend if the original data shows a linear trend. In Stata, we can easily adjust the VAR function to estimate a VAR in first differences. In the VAR command shown here, we have changed the variables to d.e, d.prod, d.rw, and du. The d in this command implies a first difference of the variables. Similarly, we can specify d2.e, d2.prod, d2.rw, and d2.u to take the second differences of the variables. As mentioned earlier, we reduce the number of lags by 1. Hence, we specify 1 lag because we are taking first difference of the variables. Moreover, we remove the trend because the original variables indicated a linear trend which is eliminated after taking the first difference. This function will automatically estimate and report the results of the VAR model and differences. Again, the VAR and first differences will give us short-run estimates. Thank you for watching, and I will see you in the next tutorial.